Okay, the final speaker of this session is Timo Weigand from the Minds Institute for Theoretical Physics. He'll tell us about modularity of VPS invariants on elliptic fourfolds and the weak gravity conjecture. Please go ahead.
Yeah, thank you very much. First of all, I'd also like to thank the organizers for making this meeting possible. Of course, like all the other speakers and participants, I'm very sad that we didn't get to enjoy beautiful South Africa this year. But of course, it's great the meeting is taking place in this way. And I'd also like to thank my collaborators for collaboration on the work I'm going to present here, Songju Lee, Wolfgang Lerche, and Guglielmo Lockhart. So the aim of this talk is to understand the modular behavior of elliptic genera of strings as they appear in four-dimensional n=1 theories. And these will be strings whose worldsheet theory has 0,2 supersymmetry. Such strings could be, for example, critical heterotic 0,2 strings of 4 dimensions, but also 4-dimensional non-critical strings. And I hope I'll convince you that this topic is a typical example of the beautiful interplay between mathematics and physics as mediated by string theory, and which is of course the topic of this meeting. So on the mathematics side, first of all, we will make contact with the theory of Quasi-Jacobi forms. I'll define this later on in the talk, which are also of interest in arithmetics. Then from the physics perspective, we will be using string dualities, including mirror symmetry, to actually compute those elliptic genera. And we will compute them by, in turn, relating them to Gromov-Witten invariants on fourfolds. So unlike the topic of Gromov-Witten invariants on threefolds, which would be relevant for strings in 6 dimensions, this topic has been studied much less, at least in the physics literature. But finally, there will also be a lot of physical conclusions that we can draw. One aspect would be the quantum gravity conjecture, the weak gravity conjecture more precisely, and I will very briefly at the end mention this. So let me give you the main results of the talk in a nutshell. The first point is that we can use mirror symmetry and string dualities to actually compute, to explicitly compute the elliptic genera for strings in 4-dimensional n=1 theories, so with minimal supersymmetry. And this includes, in particular, strings which are non-perturbative, for example, heterotic strings in non-perturbative NS5 brane backgrounds, or non-critical strings. Second, from this computation, we will observe that these 4-dimensional elliptic genera behave very differently from their counterparts, from the counterparts of elliptic genera of strings in 6 dimensions. In particular, the elliptic genus is not just a modular form or Jacobi form, as you might expect. It has such a component, but in addition, it includes the derivative of a Jacobi form, in this case of weight -2. And this derivative is something that was surprising to us. It makes contact with known results in the mathematics literature. And it also has important physical implications. I will briefly mention applications of this in the context of anomalies for 4-dimensional n=1 theories, and as said already, for the weak gravity conjecture as one example. So these will be the 3 main points which I would hope you to take away. So the strings that I'm going to discuss are constructed originally on one part of the duality chain, on one side of the duality chain as solitonic strings in 4-dimensional F theory. So 4-dimensional F theory is for us now the laboratory in order to define those strings to begin with. F theory, therefore, as you allow me to quickly review, is a compactification, as you all know, of type 2b string theory with non-perturbative 7 branes. It's compactification where the compactification space, Bn, is non-Calabi-Yau because of the 7 brane back reaction. It's the base of an elliptic vibration, which in turn is Calabi-Yau. And the 7 branes wrap devices on this base, which can be mathematically identified with the discriminant locus of the elliptic vibration. However, in this talk, I'm not going to focus on the 7 brane sector, but on another important sector, the 3 brane sector. More precisely, we are going to consider the 3 branes wrapping a curve on the base of the elliptic vibration. this gives rise to a string in the extended directions. And these are precisely the, in general, solitonic strings that we would like to compute the elliptic genus for. For instance, if we consider compactification to 6 dimensions, so on an F-theory elliptic fibration, which is a threefold with base B2, then those strings have been studied in great detail in the literature. You're all very well aware of their importance. These are the BPS strings of 6-dimensional n equal 1, 0 supergravity. For example, if the curve wrapped by the D3 branes has a negative self-intersection, then these give rise to the non-critical strings, which are an important feature of 6-dimensional SCFTs, which have been discussed already and will be discussed more also tomorrow. And if the self-intersection of the curve is 0 or positive, then we get strings which are not strings of SCFTs, but which are also interesting from the supergravity perspective. For example, if we compactify on an S1, they will correspond to black holes in 5 dimensions. So these strings are very familiar and they have been studied a lot. And we will, of course, build heavily on the insights found in 6 dimensions. So we, by contrast, are going to be concerned with strings in compactifications to 4 dimensions, 4-dimensional n equal 1, so 4 supercharged compactifications of F-theory. Now, this is defined in terms of an elliptic Calabi-Yau fourfold, and the base is a threefold. But still, the strings arise by wrapping a D3 brane on a curve on the base. And the curve on the base will be denoted by C0. Now one can get general information about at least the field content of those strings by reducing the theory on the D3 brane. This is, if we start with a single D3 brane, say this would be U1 n equal 4 super Young Mills, which then has to be reduced. One has to invoke a topological and in fact a duality twisted, topologically and duality twisted reduction because of the variation of the gauge coupling. And in the end, one finds that these strings in their worldsheet theory are a theory of n equals 0,2 supersymmetry. The modes on the string first arise from the sector of dimensional reduction of the Young-Mills fields. But in addition, there's an important extra sector. This arises at the intersection of the curve wrapped by the string and the divisor wrapped by the 7 branes. At this intersection, there are new degrees of freedom, 3, 7 modes. These are charged under the 7-brane gauge group. And this, in fact, shows that the 7-brane gauge symmetry becomes the global symmetry or flavor symmetry of the string because of these charged modes which arise at the intersection. Just as an example, for instance, suppose that the base of the elliptic fibration emits by itself a rational vibration, so a P1 vibration. This would be just an example. So here I'm drawing now not the elliptic vibration, I'm just drawing the base B3 of the elliptic fourfold for a particular type of geometries. Then the rational P1 fiber, the generic fiber, once wrapped by D3 brane gives rise to a string with trivial normal bundle. And it turns out that this string is, of course, precisely a heterotic string. It's the critical 4-dimensional heterotic string of the dual heterotic theory. And one can explicitly see that there's an E8 times E8 or SO32 current algebra on the string because of the extra 3-7 sector. On the other hand, if this C0, if this P1 can split into, say, 2 curves in this fashion here, wrapping a D3 brane on one of these 2 curves gives rise to what one would call a 4-dimensional non-critical E string. So E strings arise in this way in 6 dimensions, as is very well known. And you could view this as the 4-dimensional generalization of the concept of E strings, which have just an E8 current algebra. But these are just 2 examples. In principle, you could imagine wrapping any curve on the base and you will get a string with 0,2 supersymmetry on its worldsheet. Now, we said that the flavor or the global symmetry group on the string is the gauge group on the 7 branes. And therefore, we do need to spend at least one slide or only one slide on the gauge group on the 7 branes. And for simplicity in this talk, I will focus on models or on situations where the gauge group is as simple as possible, just a U1 factor, just to make things simple. But everything can be generalized to more complicated non-abelian gauge algebras. Therefore, I have to quickly remind you of the geometry that arises here, some aspects we will need. So in order to get a gauge group U1 in F-theory, the elliptic vibration has the following structure, or the genus 1 vibration has the following structure. First of all, it's an elliptic vibration, already said it. So we have a section, a zero section, and we have an additional rational section, another map from the base into the full Calabi-Yau. And the important point is that one considers essentially the difference of the rational section and the zero section. That's called the Shioda map. In fact, there should be a minus sign. Take it with a minus sign, everything here. There's a typo, sorry. And this difference of sections, this gives rise to a divisor in the fourfold, and therefore to a U1 gauge symmetry. Why? This is most easily seen if we invoke duality with M-theory. If we compactify M-theory on the fourfold, then we get the U1 symmetries by expanding the M-theory threefold along the divisors. And the particular divisor given here by the Shioda map, or the difference of the two sections, this turns out to be the one that gives then rise to a U1 gauge potential also in the F-theory. So we have, by an extra section, we have an extra divisor class. Therefore, we also need to have an extra dual curve class. And the extra dual curve class is drawn in this cartoon here. We have an extra class in the fiber. This class in the fiber of the elliptic vibration is intersected by this divisor sigma once. And since the divisor sigma is associated with the U1 charge, we interpret this as counting the divisor sigma is associated with the U1. We interpret this as counting the U1 charge of an M2 brane wrapping this curve. So this is all you need to take out from this. We have gauge group U1 on the 7 branes. This is flavor symmetry group U1 on our strings. And this implies in particular that there's a certain class in the fiber C5 from now on, which is associated with matter charged under the U1. Okay, so this concludes our little crash course on the geometry that we will actually need. And we can now turn to the main point of this talk, namely the definition and then computation of the elliptic genus. So recall we are interested in the elliptic genus of strings obtained by wrapping a D3 brane on a curve on the base, solitonic strings in 4D n equal 1. The elliptic genus, of course, is an object that is well known to all of you. It's essentially a part of the full partition function, or it's the partition function over the subsector with Ramond-Ramond boundary conditions if we wrap the string along a torus. And most importantly, with a -1 to the f, the fermion number inserted. So this is really an index-like partition function. It counts with signs. When we take this trace, of course, as always, we weigh the states with the left and right moving energy along the string. And we also weigh it with all the excitations with the U1 charges. U1, because this is now the flavor symmetry that we're looking at. If we have a more complicated flavor group, then we would have to include all of those if we want an interesting result. So we include a fugacity parameter, Z, and Xi is e to the 2 pi I Z and appears inside the trace. Just like Q is e to the 2 pi I tau, with tau, the complex structure on the worldsheet T2, as always. And let me stress that this refinement is really crucial because, as it turns out, for 4-dimensional elliptic genera in 4D n equal 1 theory, the elliptic genus is 0 if you do not include the refinement. This is just a consequence of the modular properties that we will see. So this elliptic genus, of course, just to finish off the definitions, then is a generating function for the degeneracies of the string excitations, with the understanding that we're in the Ramond sector and have inserted a -1 to the f. So it's an index, essentially. And I'd also like to point out that the object that we will get will in general be meromorphic in Q. Why? Because we have to face a vacuum energy along the string. The vacuum energy can be negative. This is how it is computed, C0.k bar in the worldsheet theory. So we expect something meromorphic for the elliptic genus. Now let us compute it. As I said, there has been already a tremendous literature on elliptic genera of 6-dimensional strings. So let me devote 2 slides to briefly reviewing how we can use, or how these authors here have used dualities in order to compute the elliptic genus of 6-dimensional strings in string M and F theory. So the general idea is that we start with F theory compactified now, as we said, to 6 dimensions, but on an extra S1. And this, of course, is dual to M theory compactified on the Calabi-Yau threefold to 5 dimensions. And in this, an aspect of this duality is that if we consider a BPS string in 6 dimensions, but now wrapped on the S1, this gives rise to a BPS particle in 5 dimensions, of course. To define or to describe the wrapping, we need to specify the wrapping number and the KK momentum along the string. And the corresponding modes map under the duality to particle-like modes, which we identify with M2 branes wrapping this combination of curves, namely wrapping number times the curve C0 on the base, plus KK momentum number N times the full fiber E tau. This blue object here should be the full fiber. And of course, we can invoke a relation between momentum and KK on the one hand and the excitations of the string. And in the sequel, we will set the wrapping number W equal to 1. So we will be talking essentially only about a single string, and then we can essentially identify the excitation level with the KK momentum by this relation. So this is the elliptic genus as we'd like to compute it. And more precisely, the duality states that conjecturally and confirmed in many, many examples, the index-like degeneracies in the elliptic genus should now map to the BPS invariants of the M2 branes, which correspond to the wrapped string states. More precisely, to the 5-dimensional genus 0 BPS invariants associate counting M2 branes wrapping the curve C0 once, because wrapping number is 1, and then N times the full fiber, and R times this extra fibral curve. This is why I had to introduce this extra fibral curve 3 slides ago, because this is the one that keeps information about the charge. So if we look at the degeneracies in charge sector R, this corresponds to BPS invariants counting M2 branes wrapping, in particular, R times the fibral curve C fiber. And furthermore, the last step is that for primitive base curve C0, so if this C0 is not itself the multiple of another curve C0 primed, then these BPS invariants in 5 dimensions, or Cooper-Kummer buffer invariants, they coincide with the Gromov-Witten invariants, and the latter can be computed by a mirror symmetry for threefolds. So the elliptic genus is therefore related to the partition function of the topological string on the threefold. So this is a very beautiful story in 6 dimensions that allows us to actually compute using this chain of dualities the elliptic genus, and also study, of course, its modular behavior, among other things. Now, what we'd like to do in this talk is apply similar reasoning to elliptic genera of strings in 4 dimensions, in 4-dimensional compactifications of F theory. And of course, the natural assumption, or the natural conjecture, is that also the 4-dimensional elliptic genus and its degeneracies here can be computed via quote-unquote 3D BPS invariants associated or suitably counting in a suitable manner M2 branes wrapping this curve CNR, which was the same type of curve that also appeared in 6 dimensions. After all, we're just going down further 2 dimensions. So more precisely, the conjecture is that if we consider a string, a solitonic string, wrapping a class in the base, now on the fourfold, so on the base threefold, which is primitive in the sense that it's not the multiple of any other curve class, then these degeneracies that appear in the elliptic genus, they should be the genus 0 Gromov-Witten invariants for type 2A, essentially for the curve C and R given in this fashion. But we have to specify now, and this is now where lots of the meat will be buried. When we talk about genus 0 Gromov-Witten invariants on fourfolds, we have to say that these are computed with respect to a certain choice of flux, certain background flux G. So the degeneracies are related to genus 0, conjecturally related to genus 0 Gromov-Witten invariants on a fourfold in the background of a certain flux. And there are two ways to understand why the flux should play a role. First of all, from the physics side, because if we look at convectification on a fourfold, then it's known that to really define that convectification, we have to choose background flux, both in F theory and in M theory, and then also in type 2A if we go via mirror symmetry. The appearance of the background flux can also be understood just at the mathematical level from looking at how the chromophyton invariants are actually defined. So let me briefly recall this well-known material for you. As you all know, the genus G chromophyton invariants on a general Calabi-Yau K-fold, these count stable holomorphic maps from a Riemann surface of genus G into the target space manifold YK. So the genus G Riemann surface is mapped to some curve class C, say. But in addition to saying that this is a stable holomorphic map, we also have to fix a certain number of points on the Riemann surface. And these maps will be counted subject to a certain incidence relation. In other words, we say that we look at those stable maps such that these n fixed points on the Riemann surface lie within certain cycles in the target space manifold. These are cycles AI. So when we talk about chromophyton invariants, then as you know, we always have to also specify the number of fixed points and the incidence relations. This is part of the defining data for the chromophyton invariants. Now the expected or virtual dimensions of those maps, of the moduli space of such maps, is given by this blue formula here. For Calabi-Yau, it's given by dimension of Calabi-Yau -3 times 1 minus G, G being the genus of the Riemann surface, plus N, N being the number of fixed points. So of course, for K equals 3, if we were looking at invariance on a threefold, this would mean that the virtual dimension is 0 plus N. So we don't even have to specify, if we specify 0 points, N equals 0, then the virtual dimension of the moduli space is 0. So this corresponds to isolated points. And this is why we would be counting actually curves, so to speak. But on a fourfold, and this is the difference, now K is 4, so the virtual dimension is 1 plus N, and the number of points. So even for N equals 0, we would not get a zero-dimensional object, so we can't associate with this a number of curves naively. Rather, what is natural to consider instead is for G equals 0, to fix 1 point, N equal 1. Then we have a moduli space which has 2 complex dimensions. And in order to get a number out of this, so to speak, we have to integrate a 4 form over this 2 complex dimensional moduli space in very rough terms. So in other words, we have to fix 1 point on the Riemann surface subject to an incidence relation that this point sit on a real 4 cycle on our manifold. And the actual genus 0 invariant is then obtained by essentially pulling back the flux, the 4 form class dual to this 4 cycle, pulling it back onto the moduli space and integrating it over the fundamental class associated with these maps. So therefore, this was just a review of well-known mathematical facts that indeed specifying a 4 form is intrinsic to specifying the genus 0 invariance on Calabi-Yau fourfolds, different from Calabi-Yau threefolds. And the physical interpretation of this 4 form is, as we said already, as the background flux, which appears both in F theory and in M theory. So the proposal would be that we can compute these degeneracies of the 4-dimensional elliptic genus by computing, quote unquote, the 3D BPS invariants. I don't really want to define what this is actually supposed to mean, but in the case of a primitive base curve, I should really be saying here a genus 0 chromophyton invariants. And these in turn can be computed by mirror symmetry. So the elliptic genus therefore can be explicitly computing by using the technology of mirror symmetry on fourfolds. And in this way, one can obtain very concrete results, as I said, even for strings which would be non-perturbatively defined. For example, heterotic string with NS5 branes, as long as it is mapped to good F theory by a duality. So in order to set up, so that's our next task now. So I hope you're still on this journey. So F theory in fourfold, strings, we say elliptic genus of the strings has degeneracies. Degeneracies are computed by genus zero chromophyton invariants on the fourfold in a certain background flux. And these in turn are computed by mirror symmetry for fourfolds. So mirror symmetry for fourfolds is much more complicated than for threefolds. And the reason is, among other things, the appearance of the background flux. The flux in the supersymmetric situation takes values in 2,2, in H2,2 of the fourfold. And this space decomposes into a direct sum of mutually orthogonal spaces, the primary horizontal subspace, the primary vertical subspace, and sometimes a remainder. The horizontal subspace is the one that can be obtained from the unique 4,0 form by a variation of hot structure. And this has a non-zero pairing with omega 4,0. So from here, if we have a background flux of this type in type 2A, then we would get, so to speak, a superpotential for the complex structure moduli. The vertical subspace, primary vertical subspace, is given by tensoring or by wedging essentially to 1,1 forms. This one has non-zero overlap with 2 copies of the Kähler form, but no overlap with 4,0. And as I said, sometimes there is a remainder, but I'm not going to discuss this. So mirror symmetry for fourfolds then works by exchanging a pair of mirror manifolds, X and Y. On X, one can specify a flux, a background flux in H22 horizontal, and this is mapped under mirror symmetry to a flux in H22 vertical. And the Guckow-Fafavid superpotential or prepotential that is induced by the horizontal flux on X is mapped by mirror symmetry to a prepotential, so to speak, in the A model, if you like. So this has a classical piece, which I'm not writing down, J wedge the F, plus then higher order corrections. This is where all the instanton corrections appear, and in particular the BPS invariants and then chromophyton invariants. So by setting up this mirror computation, one can do, as is the case also on threefolds, do exact computations on the world sheet in the B model, and then map it, so to speak, to the A model, if you like, and read off the BPS invariants and then chromophyton invariants by an expansion. Oops. Okay, so this was what this flux is from the perspective of type 2A. But recall, we are not really doing type 2A on fourfolds. We are just using this as a tool in order to extract these BPS invariants and then chromophyton invariants. We are really looking at the physical problem that we are really looking at is F theory on the Calabi-Yau fourfold. And as it turns out, when we look at F theory on the fourfold, not all those fluxes in H22 vert can actually be considered as backgrounds. More precisely, if we want the fluxes to uplift between M and F theory to something that preserves 4-dimensional Poincare invariants, then only a certain class of such background fluxes can be looked at. This is unfortunately a technicality that I have to point out because we will need it. So the point is that we need to make sure that the flux does not have a leg along the 4th direction if we go from M theory in 3 dimensions to F theory in 4 dimensions. And to prevent this, we need to make sure that the flux satisfies so-called transversality conditions. The details of this may be not so interesting for you, but in any event, note that this vertical subspace, which is where we are computing in the A model, in turn, again, enjoys a decomposition into 3 spaces. And the first and the third space are perfectly fine fluxes in type 2A and in M theory, but they do not uplift to something Poincare invariant in 4-dimensional F theory. So I will not switch these on as a background in F theory. And the flux here in the middle, that's the flux that can also be considered as a background flux for F theory. More precisely, in the context that we are, this flux is precisely the U1 flux, the gauge flux associated with the U1 gauge symmetry on the 7 branes. So this flux takes the form Shioda map. This was this difference of the 2 sections, if you recall. Wedge the pullback of any divisor from the base. So on the base, we can choose a divisor. We pull it back to the fourfold. This gives another divisor class. We wedge this with the difference of the two sections. This gives a 2,2 form, and this is the U1 gauge flux in this description of MF. And this is the flux that we're going to consider from now on. So the task is consider a string in F theory by wrapping a D3 brane on a curve on the base in the background of U1 flux of this type. So we have a U1 gauge group on the 7 branes. We have switched on a gauge background for this theory. And as we will now see, the elliptic genus computed in this way has properties which can be summarized in one sentence by saying that the elliptic genera are quasi-Jacobi forms. So the naive and, as it turns out, wrong expectation would first of all be that the elliptic genus shares very good modular properties just from the fact that, of course, the elliptic genus is defined on a torus, so it should transform well under modular transformations. And this is true, but not quite as naively in 4 dimensions as one would have thought. So the naive expectation would be that everything should work like, for example, in 6 dimensions. For instance, if you consider a perturbative string in 6 dimensions, then it is very well known that its elliptic genus transforms as a meromorphic Jacobi form. So a Jacobi form is like a modular form, but has an extra fugacity index, in this case, the index Z here. And I'm showing the transformation behavior under SL2Z. So such a form is defined by its weight, and the weight in D dimensions would be minus D minus 2 over 2, and by a U1 fugacity index M, which we will discuss in a second. So for 6-dimensional perturbative strings, this is a classic result, ancient result, that elliptic genera have objects in the ring of Jacobi forms. And this is very practical because Jacobi forms, of course, this is a freely generated ring and generated by the Eisenstein series. And then 3 further, for example, I'm choosing those basis elements defined via Jacobi theta functions. However, this simple statement is unfortunately not true. One reason we know already from 6 dimensions, and the other reason is now new to 4 dimensions compared to 6 dimensions. So already familiar from 6 dimensions is the fact that there can be a modular anomaly for the transformation behavior of the elliptic genus. And this occurs in our language whenever the curve on which the string is wrapped can split up into the sum of 2 or several holomorphic curves. Or in other words, if the string is really the bound state or can break up into individual strings. For example, a heterotic string could break up into 2 E strings. If this is the case, then, as has been discussed in a large corpus of work in 6 dimensions, then the elliptic genus is in fact only a quasi-modular Jacobi form. This means that in addition to E4, E6 and the others, we also need the Eisenstein series E2. In other words, the elliptic genus has a modular anomaly under a modular transformation. It picks up an anomalous term. This modular anomaly can be translated into holomorphic anomaly by, instead of working with E2, which is non-modular but holomorphic, we can work with E2 hat, which is, as it turns out, modular but not holomorphic. And what one finds, therefore, is in fact, as predicted by the famous BCOV holomorphic anomaly. This is true in 6 dimensions, and it will continue to be true in 4 dimensions whenever our string is really a bound state of more elementary strings. But, and now we come to the main point, the main punchline, there's a new and an extra feature for the 4-dimensional elliptic genus, which is not present in 6 dimensions. And this is the fact that the elliptic genus includes not only the quasi-modular piece, but also the derivative of a quasi-modular piece. So naively, we would have expected it just to be a quasi-modular Jacobi form, in this case of weight -1. But in addition, we must allow also for the derivative of a modular form of -2. And this is something which could, for example, in principle be an elliptic genus in 6 dimensions. And this is in fact, according to our findings, the general structure of the elliptic genus in all the cases that we have studied. So it is a sum of a quasi-modular piece and the derivative of a quasi-modular piece. Both of these are in general meromorphic. This, as I said, has to do with the fact that we need to allow for the 0-point energy to be reflected properly. And in order to specify these functions, we need in particular to specify the U1 index or the fugacity index. As for strings in 6 dimensions, these are related to the Toft anomaly on the world sheet with respect to the U1, and they can be computed geometrically in our case as a certain intersection number where B is what's called the height pairing associated with the U1. So this is not too important for those not interested in the geometry, but everything can in fact be translated into geometric terms. Okay, so the message is again this pretentious little equation in the box, the extra derivative piece. So why would such a derivative piece occur? Let me give you a simple geometric argument. And the argument I'd like to make is, again, using the relation to Gromov-Witten invariants. So recall what Gromov-Witten invariants were. These are invariants of stable maps from an n-pointed Riemann surface into the Calabi-Yau fourfold, subject to n incidence relations. The endpoints have to lie on these n cycles AI. In our case, we are interested in the situation with 1 point fixed, where the cycle is a 4-cycle dual to the flux. And we said we take only the U1 flux, sigma dot pi star d, d a divisor on the base. Now, suppose we look at the special case where this divisor does not intersect the curve C that we are talking about. This is only a special case, but in this case, it's very clear what happens. Because now geometrically, 2 things can happen. Either the 4-cycle G carry dual to C to G and the curve C are always disjoint. In that case, the Gromov-Witten invariants are 0. Or the curve C is contained inside the divisor pi star D for suitable members in the family, if there are any. If this is the case, then the incidence relation due to this divisor here simply localizes the result onto the invariance inside the 3-fold obtained by restricting the 4-fold to this divisor. So this 4-fold invariant, then in this special case, it's really just a 3-fold invariant. This 3-fold is an embedded 3-fold inside the Calabi-Yau fourfold with 1 extra point fixed, subject to incidence relation of this divisor. And now one can use a trick. This is just the well-known divisor equation in Gromov-Witten theory, to rewrite this Gromov-Witten invariant in terms of the invariance on 3-folds without any points fixed times an intersection number. So in other words, in our case, for the U1 flux, we therefore, if this extra condition is satisfied, get the product of this intersection number times a 3-fold invariant. But this product is just the charge R, the U1 charge of the state, because sigma with the curve in the fiber that we talked about, this curve C fib, this precisely gives the U1 charge. So the 4-fold invariant is the charge times a certain 3-fold invariant. And therefore, it's clear that if we look at the generating function, which after all is the elliptic genus, we pick up a derivative, a psi derivative, to account for this extra charge R. So we see that we can, in elementary terms, understand first the appearance of a derivative piece, and second, see that these derivatives are associated with invariants of certain embedded 3-folds inside the fourfold. This was true for this special class of fluxes. More generally, it is not true that the derivatives are necessarily associated with 3-fold invariants, but it is always true that we can add, that we have a sum of this form as given here, and that the derivative term has a closed form expression. It can in fact be written in terms of the invariance for a certain -2 flux. These are the fluxes which I actually didn't want to consider. They are not the background in F theory here, but it's just an auxiliary form of rewriting these invariants. And this is an agreement with a general formalism that was developed in the mathematics literature, in particular in the work by Oberdijk and Pixton. Okay, and final piece of mathematics, and then we come to 2 applications, and then we're done. These forms that we get now, so a quasi-modular plus a derivative, are in fact inside the ring of so-called quasi-Jacobi forms. A quasi-Jacobi form is something which can be made Jacobi by adding relatively harmless non-holomorphic or almost holomorphic functions in this way. For example, E2 is an example of a quasi-Jacobi form. And in fact, as it turns out, also a derivative of any Jacobi form as such can be turned into something modular by adding a non-holomorphic piece, and therefore it's by itself quasi-Jacobi. So this makes contact with this literature in the mathematics, on the mathematics side, and explains why elliptic genera are really, in general, meromorphic quasi-Jacobi forms. And in particular, again, we can replace, as I said, this derivative by a non-holomorphic covariant derivative, such that the full object is non-holomorphic but modular, and then enjoy instead a holomorphic anomaly equation, which is the analog of the holomorphic anomaly equation, which one gets when the string is the bound state of several strings in 6 dimensions. But this is something that appears in this form for 4-dimensional strings. Okay. Just 2 more remarks. We discussed this in a number of examples as well. For example, for instance, if I go back to this cartoon of how the heterotic string appears, one can find a close expression for the elliptic genus. If you give me 30 more seconds, I'm almost done. Thank you. So one finds, one can find closed expressions for the elliptic genus in concrete examples. For the heterotic string that appears in such F-theory constructions, in fact, the genus 0 invariants, which appear with the derivative, are non-color, in general, non-color Bayard threefold invariants. And their appearance can be interpreted physically. The elliptic genus, of course, knows about anomalies, in particular for the heterotic string as a special example. It knows about the Green-Schwarz counter terms. And very roughly speaking, the physics interpretation is that while the usual modular piece in the elliptic genus accounts for the Green-Schwarz terms associated with the universal 10 dB field as in 6 dimensions, the derivative pieces account for extra B fields and their contribution to the Green-Schwarz mechanism. So there's a clear physics interpretation associated with these derivative structure. And for more information, please ask me later. This can also be computed for non-critical strings, say for the E string. And finally, I'd like to conclude by pointing out the original motivation, at least for us, to study these structures. The original motivation was that we wanted to prove the weak gravity conjecture in F-theory. The weak gravity conjecture states that there should exist some, or in fact, a tower of states which are super extremal, whose charge to mass ratio is bigger than the charge to mass ratio of a corresponding extremal black hole in that theory. And if you try to prove this or check this in F-theory, then you find that indeed in every weak coupling limit, and this is where the weak gravity conjecture should hold a priori, in every weak coupling limit, one finds a asymptotically tensionless solitonic heterotic string, whose excitations then give rise precisely to this tower. So the states that we count by the elliptic genus are precisely the states which should appear in the weak gravity conjecture. And indeed, the modular properties, the derivative structure and the full modular properties of this elliptic genus allow one to quantitatively check that the super-extremality condition is satisfied for a tower of states. So from that perspective, this mathematical analysis and geometric analysis was really crucial in order to make contact with these quantum gravity conjectures. And with this, I'd like to thank you for your attention.
Thank you very much. I'll invite everyone to clap.
Timo. I have a question about the F. So if you turn off the flux, I assume that the elliptic genus vanishes. Is that the case?
That is the case, yes.
So this resonates with some work actually we did together related to the superpotentials being generated or not for F-theory and elliptic fourfolds, where if you don't have flux, you can have no flux or no branes if Euler characteristic is 0, and those are the special cases where the superpotential can vanish, where it's a hidden higher supersymmetric theory. do you see any relation between elliptic genus of strings and superpotentials? Is there, it seems, because this link is a bit, in that sense, in other words, elliptic genus being non-zero being correlated with superpotential being non-zero.
So for sure in the formal sense, because the elliptic genus is computed via the, by looking instead of at type 2A theory on the Calabi fourfold. And there, of course, if we have no flux, then we also have no superpotential in the type 2A theory. And the superpotential is precisely what allows, or what incorporates the degeneracies in terms of the PPS or comma-fit invariants. So from that perspective, if we go to 2 dimensions by the duality, it's obvious and indeed correct that one necessarily has this flux. Now from the 4-dimensional n=1 perspective, I mean, not having any flux will not enhance the supersymmetry, of course, of the F theory. So I'm not sure if one can argue by enhanced or by a secret enhanced or a pseudo supersymmetry that the elliptic genus should vanish.
So a related question is that the computations of the elliptic genus that you're doing, does it have any bearing in the computation of superpotential in 4D? That's, in other words, are the objects related in some way?
So I should also stress we look at F theory in terms of the primary vertical flux. This is the flux, not the flux that gives directly a superpotential, but which is mirror to it. So the physics of the flux background is to instead induce a D term. So from the direct 4-dimensional perspective, we should rather think about a D term as appearing. And here there is a direct physics connection. As an example, consider the situation where the curve is a heterotic curve, just as an example. Then, as we saw, the elliptic genus is related to the appearance of an anomaly. Now, an anomaly appears precisely when there's a Green-Schwarz term and precisely when there's also a D term, because the gauging and the appearance of Green-Schwarz terms in 4 dimensions are related and in fact equivalent. So the physics is really more that of the D terms directly in F theory. But by mirror symmetry, the superpotential plays a role then in 2 dimensions, as we said.
Okay, thank you.
Thank you.
Whitmore?
Yes, I was wondering what you can say about deriving these modular properties for general elliptic genera of 0-2 theories, just from the point of view of conformal field theory. So, I mean, there's very, very nice and simple arguments that for 2-2 theories, you get a Jacobi form.
Yes.
Within the context of conformal field theory. So let's see, so here you have an insertion of the fermion number.
Yes. I'm not sure if, is it still visible?
Yes, it's visible.
Okay, good, thanks.
Okay, so I was just wondering if you can derive this modular transform. Yes, there we are. And D is what here?
D is the number of dimensions. In our case, this would be 4, so we would have -1 to the F times F. In 6 dimensions would be F squared.
I see. Okay, so that insertion of F is surely part of why you're getting derivatives.
Yes.
If you exponentiated the F, I'm thinking if you exponentiated the F, you would get some kind of modular behavior, but then you're taking a derivative and equal to 0. Is there? Anyway, have you thought about, just as an abstract question about 0-2 conformal field theories, how to derive this modular transformation behavior as something you would expect?
Yes, this is a very good question.
You did the calculation and then you found from the algebraic geometry, you found that it had this structure.
That's right.
And I was wondering if you could derive that structure from 2-dimensional conformal field theories.
Yes. So unfortunately, we have not derived it from that structure. We would have loved to derive it from that structure, and I think it should be derived from that structure. So this would be a great thing to do. So we thought, for instance, in this process, we thought the simplest case would again be the special situation where that string is a heterotic string, where we would have criticality and we would know most. And there we have some hints why things work differently for general fluxes, for general flux backgrounds. But we have not been able to really pinpoint it into something. So the point is again related to the appearance of D terms. So we have some vague ideas what should be going wrong in the 0,2 field theory in those cases where we have these derivatives for the heterotic case, but it's still very vague, and I'd be happy to discuss this more and hear your opinion. But short answer, we have not been able to derive it yet, and it's definitely something that should be done.
Okay, David Morrison.
Can I ask a question?
Sure.
So just to summarize, if you were integrating divisor classes, am I right that there would be no derivative terms, but the thing that the partition function still has modular properties? Let's say genus 0 occurs with no marking.
Good. So genus 0 for Calabi-Yau fourfolds, genus 0 with no marking is not an invariant, but it's just a class. It's a grammar-fitting class because the dimension would then be complex dimension 1. Yes, but couldn't you then be integrating some kind of codimension 1 class, like a divisor class in the fourfold? This is complex dimension. So, well, but you have no marking. So that's the point. I mean, this you can always do. Of course, you can always add 1 point and 1 divisor, always. But here you have already complex dimension 1 without a marking. So you wouldn't know how to do this evaluation map because you haven't marked a point.
Pull back a divisor on the Calabi-Yau fourfold. You pick a divisor class of some threefold sitting in it, and then pull it back. That's codimension 1. You can integrate it against your degree 1 virtual cycle. No?
So my understanding was that one needs to fix a point in order to define this evaluation map first, in order to pull back. That's at least the construction that I'm aware of. But I'd be happy to discuss this more.
Thank you. Maybe I can ask later.
Okay, thanks. I'd be happy to discuss this. Thanks.
David Morrison.
What if your flavor symmetry is SU2 or some other non-abelian thing instead of U1?
We also considered SU2 in the paper for the E string, in fact. Everything goes through with the exception that the denominator gets more complicated. Let me scroll to the formula. This formula here, we see that we have these meromorphic Jacobi forms. The eta function in the denominator for the U1 case is in order to account in particular for the non-zero vacuum energy. In the case of non-abelian gauge groups, this denominator becomes much more complicated, and it needs some guesswork for how to pick it. So this is actually the difficulty in finding then explicit solutions for non-abelian groups. So in particular, these E-string example, which I didn't have time to discuss much, what we called, or what one might call four-dimensional E-string, which is just this E-string fibered over a curve. With the U1 flux only, the elliptic genus in 4 dimensions is extremely simple. It's essentially just the derivative of the elliptic genus in 6 dimensions, as is also clear geometrically. But if one looks, for instance, at the situation where the E string is inside an SU2 7 brane, then this simple structure no longer holds, and one gets extra contributions which are also not involving any derivatives. But the general structure that you get something Quasi-Jacobi stays the same. What becomes more complicated is the denominator in the explicit examples. And of course, this has as you know, there's a very elaborate classification, of course, and computation of many examples for the 60 non-critical strings. None of this has been done in 4 dimensions. So there's really a lot to look at.
Okay, I don't see any more questions. Let's thank the speaker again. And the next session will begin at 1700 local time. We're in 6 minutes.
Can I ask a question? If
I think there's another question, Vishnu.
All right, Shayar, there's a question.
I was just to I just wanted to know if you've considered the following example where you consider two K3 surfaces, both with a Nicolan involution. So you can consider the quotient of that. That would give you a the manifold that you're looking for. It would be elliptically fibered, but the only thing is that it would admit more than one elliptic fibration. And all these invariants would depend actually on that fibration. So what kind of forms do you get out of that, the Jacobi forms?
We have not looked at the example. Well, we would have to first pick, of course, a particular curve for the string. So it will depend very much on which type of string string you're picking.
Well, it probably also depends on the G form that you're choosing. The
Yes,
class.
It depends on the curve for the string. It depends on the G form, and it depends on the type of elliptic fibration. So so this means the 7-brane gauge group, if you like. It would be interesting to look at. So we've really only studied a handful of examples, but so. Of course, to get actual results, I mean, to get concrete results, what you need are the BPS numbers, a few BPS numbers, low-lying ones, and then you just complete into a Quasi-Jacobi form. So you need to be able to do mirror symmetry following the usual algorithms for that manifold. But from what you told me, I think it would be possible to do it for that example.
So, I mean, the example obviously becomes more interesting if your K3 surfaces, if both of them have a complex multiplication. So if both of them are attractive K3 surfaces and their the associated imaginary quadratic field is the same. So one would obviously be, well, one question would be, what are the Jacobi forms that show up in this case, because they would be more interesting, and there would be more choices for H22 class as well, especially classes coming from complex multiplication. But a simpler question would be, if you look at the moduli space of such fourfolds, which are basically products of K3 surfaces more out some involution, do you know what are the attractor points in on this moduli space? I think Greg might have actually proved in his paper that the attractor points are precisely where both the K3 surfaces are attractive. But
that's how I recall also from his paper with Kalosh, right? Indeed, Greg might want to comment.
Sorry, can we? I don't mean to interrupt, but we need to set up for the next speaker. We're going to have an extended question and answer session after the next talk, so maybe we can pick it up there.
Thank you.
Thank you.
So thank you very much to the speakers, to all the speakers in the session and the session chair for the first session. Edward, could you see if your screen is sharing?
Hallo. Nou, ik ben aan het gaan luisteren. Dat is goed. Dan doen we dat. Ja.
Okay.
Okay.
Okay, looks like that works.
Great.
You see my cursor, by the way?
I do.
Okay, I'll be right back.
Okay.